Okay, let's dive right into this pull request. Welcome to today's explainer. I'm stepping into the role of your senior engineer today, and we are reviewing a really clever Go script that just came across my desk for our codebase. So the main goal of this program, to elegantly handle prime factorization, which is basically breaking a number down into its fundamental prime building blocks. But the catch is, it does this entirely from scratch, without relying on standard libraries for string formatting or advanced math. It's a fantastic exercise in fundamental programming concepts, and we are going to break down exactly why this code works so incredibly well. All right, here's our game plan for this review session. First, a quick PR overview. Second, we'll look at the recursive printing helper. Third, input validation. Fourth, the core factorization logic. And fifth, we'll look at the mathematical elegance before giving it a final sign-off. Starting off with Section 1, setting the stage with our PR overview. Taking a bird's eye view of this code block, we have a very clean two-function setup. We've got a helper function called putInt up at the very top, followed immediately by our main function that handles all the argument validation, string parsing, and the actual mathematical loops. Honestly, it's super concise and readable, which is exactly the kind of thing you want to see when you open up a pull request. Moving right along to Section 2, the recursive printing helper. So, you might know our codebase uses a custom library called Z01, and it has a pretty strict limitation. It literally only prints one character or rune at a single time. This means multi-digit numbers can't just be slapped into a single standard print call. To get around this, the author is using recursion, which I love. By checking if n is greater than 9, the function repeatedly strips the rightmost digit using n divided by 10. This effectively defers the actual printing command until it hits the absolute deepest call in the recursion stack. Let's actually rubber duck this with a simple number like 13. When we call putInt with 13, it sees that 13 is greater than 9, right? So it pauses and calls putInt with 1. That putInt1 call executes first and prints the character 1. Then the real magic happens. The stack unwinds, returning back to the original call to print that remaining 3. It's a perfect way to handle printing left to right without any complex arrays. And if you look at the detailed call stack trace here, you can see exactly how that recursive call defers the action. As the functions resolve and pop off the stack, the digits 1 and 3 are pushed to the console in the correct, human-readable order. Visualizing the call stack like this is honestly just a great habit to guarantee your recursion won't just spin out of control into an infinite loop. Now, what's really cool here is the clever ASCII trick happening inside that loop, n modulo 10 plus the character 0. This basically converts the raw integer digit back into its printable ASCII rune equivalent. Because the character 0 has an ASCII value of 48, adding our integer 3 to it gives us 51, which is the exact ASCII rune for the character 3. It's a classic, highly efficient low-level trick that skips the need for heavy type conversions. All right, let's jump into Section 3, input, validation, and guard clauses. Because good code doesn't just do the right thing when everything is perfect, it actively protects itself from bad inputs. Looking at the snippet side by side with its logic map, you can see the code cleanly catches missing arguments or totally invalid strings. If the argument count isn't exactly 2, meaning the program name plus exactly 1 input string, it just returns silently. No ugly panics, no messy crashes, just a completely clean exit. It explicitly lists out inputs that trigger these silent returns. And I want you to notice bullet point 2, catching non-digit characters. This naturally handles negative numbers right out of the gate, because the minus sign correctly registers as a non-digit character, instantly returning. It also filters out 0 and 1 right at the very end, since, well, neither of those have prime factors anyway. The defensive programming here is really solid. I've got to praise this specific line too. It's the standard ASCII to integer trick for parsing the string. By multiplying the accumulating variable n by 10, it shifts the existing digits to the left before adding the newly converted integer. It is literally reconstructing the string into a real number, digit by digit, completely bypassing the need to import a heavy string conversion package. Really elegant, lightweight work. Okay, moving down to Section 4. The absolute heart of the PR, the factorization loop itself. Here we have an outer loop trying out candidate divisors, tracking the variable d and starting at 2. Inside that, we've got an inner loop dividing out d for as long as it divides evenly, shrinking our main number n as it goes. This means if a number has multiple of the same prime factor, like say the number 8 being 2 times 2 times 2, this inner loop will beautifully exhaust all of them before the outer loop ever even increments. But wait a second, looking at this code, why aren't we checking if our divisor is actually prime?
I mean, how do we know D isn't 4 or 6? Oh, right, that is implicit primality at work. It's a mathematical guarantee. Composite numbers like 6 will literally never cleanly divide n at this stage because their prime components, the 2's and the 3's, were already entirely exhausted by the inner loop earlier on. So absolutely no explicit primality check is needed, which saves us a ton of compute cycles.
Finally, Section 5, Mathematical Elegance and Sign-Off. Just to ensure this clever math actually holds up in reality, let's walk through a step-by-step trace for a much larger composite number, like 225,225. Tracking the state of D and N shows exactly how the inner loop handles those repeated factors gracefully without any extra messy logic. You can see D testing 2, failing, then testing 3, dividing it twice, and just shrinking N all the way down. The matrix completely proves the logic holds up.
And we can't forget formatting, which is a crucial point here. By only printing the asterisk separator when the remaining n is strictly greater than 1, we guarantee perfectly clean output with no ugly trailing asterisks at the end of our terminal line. It's the little attention to detail like this that really elevates code from just working to being truly professional.
What about edge cases? Well, checking the matrix, prime inputs like 9539 are handled perfectly. The outer loop will simply climb, failing the inner loop check every single time until D finally equals N itself. It then prints the prime number and gracefully exits. The logic is incredibly resilient. Overall, I'm absolutely approving this PR. It gets a big looks good to me. The developer demonstrated a fantastic grasp of low-level data manipulation and algorithmic efficiency. But as a final thought to leave for the junior dev in the review comments, without an explicit upper bound check in those guard clauses we looked at, what happens to our program if an input is provided that silently overflows the Go integer limits? It's a fun, provocative question to keep them thinking about system limits and edge cases. Anyway, thanks for joining me on this explainer, and I'll see you on the next code review.